Okay, so we'll be talking about a concept called staged reactive data pipelines, which is an approach to building streaming processing systems in a reactive style, and how Kafka provides an excellent backbone to power these types of data streams. So we've been ourselves developing a large scalable IoT platform for ingesting car telemetrics data in this style, which we've actually taken into production. So in this talk, we'll be sharing some of the things that we've learned about this architecture with you.
All right. So first off, a little bit about the company that we work for. So we're from a software consultancy company called Cake Solutions. We specialize in developing reactive and scalable software solutions using tools such as Scala and Akka with cutting-edge technologies such as Kafka and Cassandra. Traditionally, we have focused on building web services, but these days we mostly focus on these large-scale distributed systems. The company also has a large DevOps expertise using technologies such as Mesos, Amazon Web Services, and Docker. And when we're building these sorts of complex applications, the demands on this DevOps team is often as great as the one of the development team as well.
Okay, so the topics we're going to cover include an explanation of what we mean by reactive data pipelines, with a specific focus on building data streaming applications from the developer's perspective. So we'll also cover how Kafka provides the crucial infrastructure required to support these data streams in a resilient and reliable way. So we'll be giving you an overview of some of the common usage patterns for interacting with Kafka and some of the techniques used for streaming data through your systems. Finally, we'll talk a little bit about implementation choices around the Kafka driver.
Cool. So, stream processing. So stream processing is obviously quite a hot topic these days, and it's interesting to see that there's a lot of coverage in this conference for this style of data processing. So we noticed that one of the bigger drivers for around stream processing comes from the big data space, which has traditionally tackled the processing of huge data sets using batch processing techniques. But there's also an increasing demand to ingest, process, and produce data in real time.
Yeah, so typically stream processing services are described in terms of event throughput rather than query-based, as in sort of request-response type patterns we see in traditional REST web architectures. So specifically, services receive and process this incoming data, perform some kind of computation or transformation, and then produce some output to some kind of downstream sync. And specifically, Internet of Things is an interesting domain of application where significant data volumes are processed concurrently from huge numbers of potential sources, and we need to process that in sort of interesting and complex ways. So one approach to building out streaming solution is by using streaming platforms such as Apache Spark Streaming and Apache Flink, which I believe was content of one of the talks today. So these kinds of solutions provide a distributed processing infrastructure to which custom streaming logic can be deployed. So you typically develop out your custom streaming topologies, your custom logic, and deploy those up into these clusters. And it sort of takes care of some of the complexities around running these topologies, gives you support for things like clustering, data shuffling, and message processing guarantees, and so on.
Right. Another approach that we've utilized is a technique we like to call streaming from ground up. And this is something that we've seen quite a lot of people actually use. So this involves building custom streaming solutions from existing software stack using established dev processes and DevOps capabilities rather than fitting everything under a new framework. For example, we have a lot of experience in building scalable, high-volume backend services using tools such as Scala and Akka and deploying them into cloud environments. Now, this sort of approach we've taken is to leverage these capabilities, but also to build our applications in a streaming style. We will be introducing some of these architectural concepts that we've learned how to arrange these streaming applications and provide strong reactive properties to that design. So these techniques and patterns we'll be covering are essentially technology agnostic. So as I said, we've been applying Scala platform around these, but you could use pretty much whatever technologies you have available.
Okay, so when building custom streaming applications, our processing logic is typically arranged in some kind of staged event-driven manner, with our processes separated by some form of queue. So any number of processes might be able to be arranged in this kind of manner. So the stage pipeline can be viewed from the context of a single in-application node. So for example, the processes here could maybe be Acker actors, and these queues could be message mailboxes. We can imagine this kind of topology to be arranged inside an application. But also we could imagine seeing these into a multi-node configuration distributed across many nodes. So these processes might be single application nodes sending messages onto remote queues. So this architecture naturally optimizes the processing of a single stream as the stages can be processed concurrently. And it also gives us bulkheading properties. So processes can in-queue work for the next process, even when there's a downstream issue. One of these downstream components is unavailable, for example.
Right. Well, stage event-driven architecture, that's really old concept, So we prefer to think of this design as a reactive data pipeline. So what are the sort of qualities that the data pipelines require to be actually reactive? So we've considered these properties in terms of the reactive manifestos principles.
So we need our processing here to be responsive, which speaks to the latency of the message processing and also the specific ability to quickly detect and deal with failures. So resiliency requires us to provide a high availability, failure recovery, and so we need elasticity in our message processing so we can actually scale our processing when the capacity of any of these given processes or queues is reached. So the processes themselves must also be implemented in a non-blocking style for this to be a truly reactive system.
So these are the attributes that we are looking for when implementing reactive stage data pipelines. And we will be exploring some of these techniques that we've applied in order to meet these sort of requirements.
Okay, so for simple application domains, the pipelines can be implemented as an in-app process, but assuming we're dealing with complex applications here with high availability and scalability requirements, experience teaches us that a microservice-based sort of multi-node configuration is going to be needed. So each processing stage in this model is an independent microservice, usually deployed in some kind of cluster arrangement. So this provides us the opportunity to sustain the availability of a service, even given a failure of one of these microservice nodes. So in this example here, one of the microservice 1 nodes fails. We need some mechanism whereby the other nodes can actually pick up that workload. So the dependencies between these separate microservices can be defined via a schema definition. This gives us a nice separation of concerns between our processing stages and an independent deployment lifecycle between the stages in our microservices. So we could imagine a situation where we have one development team working on the microservice 2 application and deploying that and controlling that in a separate manner. So this model gives us a basic architecture for powering high-volume processing pipelines. We would also typically expect to see other less performance-critical microservices deployed around this model using more traditional communication patterns, such as a REST API for providing configuration or other query services. But in IoT or big data streaming apps, these pipelines are kind of the hot path and the critical aspect of our system.
It's also useful to highlight that when deploying complex microservice arrangements in the cloud, an operational management capability is key. So cluster orchestration services such as Mesos and Marathon, they provide the ability to deploy and manage microservice in cluster arrangement, as well as provide scaling capabilities and also automate some of the operational tasks, such as failure recovery.
So we've used Mesos and Marathon for this purpose in our applications, but there are other popular cluster orchestration tools available, such as Kubernetes from the Google. Other teams in our company have also experimented with DCOS from Mesosphere as an approach to potentially try to simplify this area. So Amazon ECS also provides a capability, and there's also Docker Swarm and others. So these types of capabilities are not strictly related to streaming applications per se, but they are an important consideration when attempting to manage these kind of complex deployments, as are having solid CI/CD pipelines and dev practices within the team, etc.
Finally, a critical part of the architecture is the messaging middleware, which conveys data between these microservices. So the middleware has to provide a reliable message handoff. Whatever the data is written into the queue can't be lost until the next stage has successfully consumed that data. It also should be highly available and provide consistent performance guarantees.
Okay, so let's introduce Kafka into the mix there. So in our applications, we've been using Kafka to provide this queuing capability with great success. So for those who don't know already, Kafka is a distributed message broker that supports parallel streaming. It also has a good set of features that closely align with the reactive principles.
So let's take a look at some of these key features so that we can get a better vision on as to how to actually build these streaming applications around Kafka. So first of all, data streams in Kafka are message-driven. Data is routed as messages to the consumer applications through logical topics which represent data categories. So in this example, we have a flow of electricity readings coming from the left-hand side, as you can see those boxes right there, to the electricity readings Kafka topic in the middle. A single message is composed of a key and a value, both of which can be any sort of arbitrary binary data. And in this example, the message for the electricity readings are sent as messages with the meter ID as the key and the meter reading as the value, right? And the messages are routed to the example consumers, the auditing service and the electric bill calculation service as shown here.
Mm-hmm. Okay, so a topic decouples a consumer and producer process by providing a reliable message handoff. This is an essential feature to provide resiliency and message delivery guarantees. So in this example, the electric meter app delivers readings to Kafka. Once Kafka has accepted this message, an acknowledgement is sent back to the client. So the meter app can now be confident that this reading has in fact been received. On the consumer side, the message is consumed and confirmed once the processing has been completed. So this is the basic mechanism for guaranteeing the delivery through our pipelines.
Kafka is of course a distributed system as well, so topics are actually physically located in one or many Kafka nodes as partitions. So a logical incoming data stream can be split into a number of these substreams, each of them which are within one of these physical partitions. This feature allows a logical stream to be processed in parallel across any number of Kafka nodes, providing elasticity to the message stream. And when using multi-partition topics, it's also important to understand that Kafka can only guarantee the ordering per partition and not across the topic as a whole.
Okay, so these partitions can be replicated to other nodes, which provides resiliency against Kafka node failures. So in the example here, we see partition 1, which is located on Kafka node 1. There's also a partition replica found on Kafka node 2. So given the failure of a Kafka node, the data can continue to be served from the partition to a consumer from this replica. So this is obviously a simplified model of typically what you'd see on a Kafka cluster, where you'd have normally around at least three nodes of Kafka, and the partition and replica counts will vary based on the use case and quality of service guarantees that you require. So these configuration options are usually specified at topic creation time.
So let's look at this partition arrangement from the consumer applications perspective. So given this multi-partition topic, we can arrange a number of instances of a consumer application to consume the topic in parallel. So each of these subscribed members of this in this consumer group will receive a subset of the data instead of the whole data from the Kafka topic. There's also a cool feature that's not really talked that much about in Kafka around automatically assigned partitions. So with this feature, given a failure of a consumer node, Kafka will notice that the consumer is no longer connected, and it will actually reassign the partition to another consumer. Now this provides us a responsive way to recover from a failure of a processing node. So when the consumer comes back online, Kafka will rebalance the partition back to the consumer. Thus, we're going to once again get full parallel utilization of the Kafka topic and its consumers as well.
So note that the number of partitions will dictate how many parallel consumers you can have per consumer group. Thus, parallelization must be designed up front. So in this example here, we have 3 partitions and 4 consumers. This 4th consumer will not be assigned any partitions. Typically, you would want to arrange your partition count to be substantially bigger than what you estimate to be the parallel consumption. So the raw performance in Kafka is one of its most remarkable features, providing a very high throughput that is linearly scalable, given this clustering model. So to give rough ballpark figures, we have observed in our application deployments a single consumer performance in the range of 20 to 90 megabytes a second of data transfer, and that will obviously scale up dramatically given an increased number of consumers. So bottlenecks in our experience tend to be in the latency of the message processing or indeed the network bandwidth availability. So Kafka really gives us a consistent high performance in message delivery.
So we've looked at some of the Kafka's key characteristics that provide the reactive capabilities we require. Responsiveness, resiliency, elasticity, and its message-driven nature. So now let's shift our focus onto the consumer applications. Let's see how we can actually extend these sort of features into these consumer applications.
Okay, so let's take a look at the Kafka consumer patterns then. So producing to Kafka is generally pretty straightforward, but on the consumer side, there's a lot of options and capabilities we need to consider. So when we first approached Kafka, we found it pretty tricky to figure out how our consumer stream should actually be arranged. So let's cover some of the common consumption patterns that we've seen in practice and how they can be applied. So the most basic consumption arrangement is to use a single partition topic and a single consumer. So this model provides us a simple queue semantics. It's kind of easy to reason with, and it has simple ordering guarantees. That is, the ordering in a partition is actually guaranteed in Kafka. So the limitation, of course, is there's no possibility to scale beyond the consumption of a single node. However, given the performance of a single partition, as we've highlighted, it's still a viable option in many cases.
So single partition topics can still be replicated, providing us high availability on the producer side. But care must be taken to ensure that the failed consumer node is restarted. For example, if the auditing node here dies, the node must be restarted or replaced for the message processing to continue. One approach is to leverage the cluster orchestration layer that I mentioned earlier to ensure that a new instance of a consumer application can be started to pick up the work of the failed consumer. Another approach that we've also used is in-application cluster mechanism to ensure that there's always a single topic consumer live within a cluster of a consumer, within a cluster of consumer nodes. Right. So for this, we've leveraged the Akka cluster. With Akka cluster, we've used the Akka sharding feature to ensure that one of those shard members is one of these subscribers, which we then launch up with a external service.
So this essentially guarantees that we at least have that one consumer for this partition within our actual application cluster level. So Kafka also provides us a fan-out semantic even for single partition topics. So in this example, the auditing and billing applications can receive the same view of the data by subscribing to the topic in different consumer groups.
Right. So now looks into how the consumers look in this sort of high-level perspective. So let's look into the internals of one of these consumer applications. So here we have a high-level example of our auditing service application, which receives messages from Kafka, performs some kind of processing or transformation, and saves the results into a database, right? So on the left-hand side, we have the Kafka partition, which our application consumes messages from. So the application uses a Kafka client for consuming these messages in batches, right? Passes the messages onwards to the processing logic. And after the batch has been processed and stored in the database, the batch delivery is confirmed back to Kafka. Now, if the service fails at any point of the message processing cycle, the messages will be reprocessed from the last confirmation. With this technique, we can actually guarantee at least once delivery through Kafka, all the way through the services, all the way to the database.
So sometimes we need to keep in mind about the confirmation mechanism is that they're not done on an individual message-by-message basis. So instead, a commit point marker is moved in the Kafka partition, which is tracked for each consumer. For example, here we have a consumer that has read a first batch of 2 messages from the Kafka partition. And when the consumer wants to confirm the delivery of this batch of messages, the commit point is then moved to the correct offset, and that's maintained on the Kafka side.
All right, so like we said, the simple message queue pattern is quite limited to the processing capacity of the single consumer. So to parallelize the processing of a topic, we can use the clustering feature we mentioned previously, the clustering from the Kafka side. So each node of the auditing application subscribes in a common consumer group. And looking at the consumer application in this cluster arrangement, we can actually see that there's no difference to the simple queue model. So the application is still the same. No additional logic is required in the application to handle this sort of clustering feature. That's pretty nice.
Yeah, so the complexities around cluster membership and partition assignment are entirely handled by the Kafka with this model. It takes this complexity away from the consumer application implementations. So it's interesting to look at this model of parallel processing from the orchestration perspective. With no dependencies between these auditing nodes, new nodes can easily be started and by the cluster management system in response to increasing demand. So new auditing nodes simply connect to Kafka, and it manages the partition rebalancing and assignment for us, assigns new partitions to this new node, and then shares out the processing. So we've now looked into a few simple models of arranging Kafka and the consumer applications using simple single partition consumers, parallel multi-partition consumers, and the fan-out pattern. But these models assumed that the consumers were performing stateless processing. So how can we do stateful processing then, while maintaining the same availability guarantees? So let's give an example. How can we implement a consumer application that calculates the average electricity consumption per meter, for example?
All right, so one of the complexities around parallel streaming of data and stateful processing is data locality. So how do we make sure that the correct data is available to the correct processing component, right? So if our aggregation app is calculating this average electricity consumption per meter, all readings for a given meter must be located on the same partition. So in a naive setup, if we just use the Kafka as it is, and we pipe events from multiple meters into the same topic, the data is randomly distributed across multiple partitions. Now this means that the aggregator nodes will then not receive all the data that they require, thus the aggregator will produce the wrong result.
So we can ensure that the data reaches the correct processing components by designing a keying strategy. So messages with the same key are guaranteed to appear in the same partition. For example, the aggregator nodes here process data for specific meters, which means we need to use the meter ID as the messaging key. So it's interesting to understand here that when designing these data streams through Kafka, we need to be thinking about the partitioning and the keying strategy depending on our processing requirements.
The state of the application can, of course, be as important as the messages that are being processed. Therefore, the state needs to have some sort of a resiliency guarantee similar to the messages as well. So, in essence, if our aggregation node fails, how do we make sure that we don't lose the state of the application? So, similar to how incoming messages are stored in Kafka, the state must also be written to some sort of a persistent store. If an aggregator node fails, we need to be able to restore the latest state in order to continue processing the stream in a consistent manner. So we've been using Cassandra for our persistence purposes, but pretty much any sort of solution works here. All it really needs to do is to be able to save some sort of a state in a persistent manner. You can even use event sourcing capabilities here if you like.
That's right. So now let's look at the the introduction of this persistent layer affects the consumer application structure. So like in the examples we've shown before, the application consumes and processes data in batches using this custom logic. After the processing done, this state is persisted to the database layer. Once the state has been persisted, only then can it confirm this delivery back to Kafka and request a next batch of data. So the persistence layer here could obviously be a journal of state changes in the kind of CQRS type model, or maybe just an update in place to a Cassandra record, for example. So there is a major downside to this approach. If a failure occurs after the state has been updated to the persistence layer, before the batch has been confirmed back to Kafka, on recovery, the unconfirmed messages will be replayed and updated against this state, so it will lead to an inconsistent state change. So the average meter reading in this example would be calculated incorrectly.
Well, we can do much better than that. So rather than relying on confirming offsets to Kafka, we can manage these offsets ourselves and store them alongside with the state. And we can do this because the offsets in the partitions in Kafka are unique. So those will remain through the life cycle of the topic, right? So during the state recovery, instead of loading just the state, we can load the latest offsets alongside the state and resubscribe to Kafka from those exact positions in the topic. And this way we can get much tighter correlation between the persisted state and the Kafka processing state. This way we can gain this sort of atomic way of dealing with these two stateful components, basically. This means that we can still have at least once delivery of data through the application, and additionally we can get exactly once state manipulation.
So looking at this stateful processing architecture as a whole, we require a shared persistence store accessible to all of our processing nodes of this aggregator microservice. So we utilize Kafka's auto partition management system here to balance and scale the topic consumption across the given number of processors, providing us a natural scaling mechanism. So in this example, partitions 1 through 6 are assigned to aggregation nodes 1 and 2 here. And given a situation where we require additional processing capacity, our orchestration service can fire up a third processing node. So Kafka will automatically balance partitions to this new node, and in this example, partitions 5 and 6 will be assigned to aggregator node 3. So on assignment these partitions to this new aggregation node, this node has the opportunity to load the latest state and the offsets for these partitions, and then request from Kafka the exact position where it needs to continue that processing. So it can seamlessly take over processing of that stateful stream from aggregation node 2. So this model kind of provides us a flexible and scalable and resilient architecture for parallel stateful computation.
So we've covered some of the basic consumption patterns and discussed their properties. So in summary, we found these 4 major consumer patterns. So for example, the single partition mode, it provides this sort of good performance and gives us strong ordering guarantees. Although, picking up the work of the failed consumer node becomes the responsibility of the consumer application or the orchestration service. On the other hand, in the multi-partition mode, by increasing the node and partition count, you can achieve massive bandwidth at cost of strict ordering guarantees. That is, you can only guarantee the ordering by partition and not the topic as a whole.
And the fan-out pattern allows us to feed the same data into multiple applications. This can be used with the single and the multi-partition topic modes. And finally, stateful processing requires us to take a more hands-on approach to managing the Kafka messaging consumption process. So this is one of the avenues where streaming frameworks might provide us some additional support. But it's not impossible to build this kind of capability yourself.
Right. So we've gone through the this consumer architecture. So now we'll be focusing a little bit on the Kafka libraries. What sort of libraries do you have out there to provide you these capabilities? So naturally you can use Kafka from any language. The only limitation is the availability of an actual Kafka driver. So it's language agnostic completely. There is support for Java, Scala, and C, and through the C bindings you can also gain support for more esoteric languages such as Haskell and OCaml, and also Python as well.
So one emerging approach is a reactive streaming approach around Kafka. So two options in this space are the reactive Kafka client developed by the Akka team and the Kafka Streams client developed by Confluent. So these models give you a kind of combinator style approach to building out your stream topologies inside Kafka consumer applications. And when we're talking about more complex streaming arrangements, these tools are really where they're going to come into their own.
Our own approach was to develop our own Kafka client that provides asynchronous, non-blocking API for Scala. We published this driver called the Scala Kafka client as an open source project. Our focus was to provide an interface that's not only too easy to use, but also supports some of these supports and simplifies some of these patterns that we've been discussing in this talk. So yeah, be sure to check it out.
Yeah, so a little introduction to our client that we built. So it's built on top of Akka. It's an API that's built on top of Akka. So Akka is obviously, as many of you are probably aware, an open source toolkit written in Scala for building highly concurrent, distributed, and message-driven applications. So we leveraged its high throughput message dispatcher architecture to allow consumer applications to be developed in a reactive style.
Right. To interact with Kafka, we provide two key actor components, the Kafka consumer actor and the Kafka producer actor, which take care of the complexities of consuming and producing to Kafka. And these components can be then wired up to your own custom processing components through active messaging. So even though you're basically still using Akka, you can still build your own processing logic in pretty much any other way. So here we have, for example, on the left-hand side, we have the Kafka consumer actor consuming stuff from Kafka, sending it on to a receiver actor, which can be of any sort of complexity. Finally, after the processing has been done, it produces some data to the Kafka producer actor, which then will confirm the delivery back to the consumer actor, which will optionally commit the offsets back to Kafka. Thus, you can pull in more data. We have found that this sort of combination of Kafka and Akka provides a really excellent platform for building these sort of custom high throughput and scalable data pipelines.
Okay, so in summary, we've covered ways to leverage microservice-based techniques for building processing pipelines using Kafka. While the streaming topologies can be varied and complex, many of the use cases fall under a small set of consumer patterns.
So we've introduced some of the challenges and requirements around building these scalable and reactive data pipelines, such as message delivery guarantees, parallelization, fast recovery, stateful processing. We've also noticed that Kafka provides an excellent backbone for these sort of resilient, high-performance data pipelines, but also first-class support for these reactive streaming features that we've covered.
So stateful processing remains a challenging area, so we explored strategies and a kind of template architecture of building out stateful processing within your application.
Finally, we want to highlight a few of the challenges that we really didn't discuss but are important in designing these data pipelines. So a good data serialization strategy is an important part of your architecture design. How can we support an evolving message protocol using binary schema definitions to provide controlled and independent updates to your whole data processing pipeline? Popular approaches for these include, for example, Apache Avro and Protobuf.
So evolving applications also pose challenges. How can we roll out application updates to our microservice with zero downtime? Another consideration is around complex streaming topologies. So what techniques around joining and splitting streams, for example? And when these streams get arbitrarily complex, how can we handle that complexity essentially?
Yeah, that's pretty much it. There's going to be another talk featuring some of these concepts that we built. Our CTO Jan is going to be talking about that. There's also a demo on our showcase there, showcasing some of these features that Jan has been building around these social patterns using our own client. So be sure to check it out. Thank you.
Yep. If anyone's got any questions. Okay, so we finished a little early, so if anyone's got questions, fire away.
This one.
Could you go back over, it's not too long, your approach to write once? I didn't quite follow how that.
Yes. The stateful processing. Yep. Let's go. Right. So the important part here is that when you're dealing with this sort of distributed system, if you have two different components where you have two different components which have some sort of state related to message processing, if you have a failure in between writing one of those data, you will get inconsistent results when you recover the processing node, right? So let's say we've updated our aggregation, we persisted the state, but we now get a failure before we actually can confirm the delivery back to Kafka, right? So instead of actually relying on Kafka as this sort of a storage for these offsets, we can actually manage those offsets ourselves and save them as part of the state. So when we recover the state, not only do we recover the state itself, but the offsets as well. Mm-hmm. So we can then ourselves dictate where do we want to consume the where do we want to continue the consumption of from Kafka. Mm-hmm. Cool, awesome. Any more? There we go. Fan out. So. Yep.
Did you catch that?
So the rebalance, so if you get a rebalance, what happens then with this sort of stateful processing? So with Kafka, you can listen for these rebalance events. And so when a rebalance event occurs, you have a chance to actually do something about it before you let that happen. And this way, let's say Kafka takes a partition from a live component. That component can save any sort of state around it into the persistent storage, and thus the next component that comes back alive can then recover this sort of state. So by utilizing some of these rebalance events, we can get the persistent storage in a consistent state for the next partition assignment.
So for example, in aggregation node 3, when it's assigned the new partitions, it actually gets a callback to say, here's some new partitions being assigned. And in that thread of activity, you will actually load the state and offsets, and then you will use those offsets and then subscribe to Kafka from that specific point. So you get these callback hooks provided by the Kafka sort of Java driver that underlies this. And you can hook into these mechanisms to provide these capabilities.
Yep.
Any more? No?
I don't see any more.
Okay.
All right, that's cool. Awesome.
Thank you very much, guys.
Thank you very much.